All right, good morning. Mr. Burkhardt here, and we are going to make these videos talking about the answer keys to the workbook. Yay! All right, it's as if I haven't even looked at it yet. So, draw what the string looks like at time t equals 5 milliseconds. So what's happening with this wave made of triangular wave pulses on a string, haha, it's fixed to the wall, and basically what's going to happen is the string is going to hit the wall and it's going to reflect, and since the wall is more rigid than the string, it should invert on itself and then start some constructive and destructive interference. It looks though what they are saying is that instead of the string inverting, oh, that's right. It's so. Oh, I see what's happening here. So a negative pulse here is going to flip over when it hits the wall, and it's going to meet this upward pulse coming in, and they're going to constructively interfere with each other at that time. So that's what's happening here. Is the inverted pulse, which is in front, is flipped and met the right side up pulse right behind it, and now they're constructively interfering with each other. And after that, it's just the rest of the wave that hasn't hit the wall yet. Wow. On the point P is a single point on the string. Blank attempts to draw a graph of the height of point P as a function of time, creating the graph shown to the right. He assumes that no energy is lost as the wave reflects off the wall. Blank's graph is correct between 5 and 7 milliseconds because the reflected pulse interferes with the original pulse, creating a flat line. Good job, Blake. The section between 7 and 9 milliseconds needs to be inverted because it's an inverted pulse. The orientation change that occurs off the solid fixed boundary. Okay, that makes sense. If some wave energy is transformed into other dissipative forms of energy, how would the part drawn? So the reflected wave would be smaller, and so the interference wouldn't be constructive as high, and there wouldn't be a flat part. There would just be a lower part. How would the graph shown in part B need to be modified? Won't be as large. I just talked about that. Okay. JKL, Carlos, Dominique, and Angela, our physics champs, are given 2 speakers that emit the same single tone in phase. The sound energy emitted by each speaker every second is also the same. The students are using the speakers to experimentally estimate the speed of sound. They set the speakers together 5 meters away from Angela, whose hair is being blown back by the speakers, and she's measuring with a sound intensity meter. Oh, I have one in my classroom. So they're moving the speakers closer to Angela, and you can see that the sound intensity is getting bigger, right, on the graph, and they plot the data of the sound intensity, and I thought we were trying to measure the speed of sound. Why does the sound intensity increase and decrease as one speaker's move closer to Angela? So the 2 speakers produce sound waves that have constructive interference. They are perfectly aligned crest to crest. The distance d is therefore an integer number of lambda when they constructively interfere with each other. All right. So if you set them up differently, they will, the separation distance will make a very soft noise because they are destructively interfering with each other. The distance d is an odd integer number of half of lambda. The frequency emitted by the speaker is 440 hertz. That's annoying. Obtain an estimate of the speed of sound. It's 352. So the wavelength is 0.8. So let's see, how did they get 0.8 for the wavelength? Well, see, we are at 1.6 here, and we are at 2.8 here, and that is 0.8. Yeah, the distance from peak to peak is 0.8, and that's how they did it. Inspector Clouseau, it must be warm. 352 is a pretty warm room. As the speaker approaches the student, the amplitude is larger. That means a larger number. Okay. Yeah, right. The minima and maxima are getting bigger because the sound is getting closer. Thank you. Now we're in part M. Blake is given the equipment listed below and asked to obtain a precise value for the speed of sound in air. It's got a meter stick, a sound intensity meter, a barrel filled with water, a pipe, a speaker who can generate a single tone. And so, you know, we don't have a sound intensity meter. We use our ear, right? Your ear could be a sound intensity meter. You can tell when something's louder and softer. But apparently, Bubba here, Blake, is going to use a sound intensity meter instead of his own ear. So basically, this is the lab that we did. He's going to put the pipe in the barrel and set the ear above the top of the pipe and align the speaker above the tube and play a frequency in the 200 to 400 hertz range. That's my tuning forks. They're all in that range. Well, some of them are 500. And move the tube up out of the water, measure distance from the top of the water. So this is basically our lab. Different values of the frequency will give data about wavelengths and frequencies. This is exactly what we did. And frequency versus the inverse of wavelength can be made, and the slope will be the velocity of sound. Right. So we could have done that. Wow, I didn't think of that. Oh, well, we were trying to find the frequencies. And so this would be a lab where you're trying to find the speed of sound instead of trying to calculate the frequencies, but it's very similar to what we did. Depends on the temperature of the air, sucker. Assuming that he has access to a thermostat-controlled air conditioning and heating for the laboratory, so not my building. It's thermostat-controlled, but I don't have access to it. Explain how the procedure outlined in Part B can be modified to determine how the temperature of air, so they're recording the temperature in the room, and then you are graphing it for different temperatures, and if the graph has a non-zero slope, then the speed of sound does depend on the temperature of the air. So you can pause and read this. Basically, you're just repeating the experiment at different temperatures to see how the slope changes at different temperatures. Sounds good. Oh, wow, there's a part N. I wonder how long it's been. Why don't we just, for the sake of our sanity, just stop here and make a new video for the next two parts.